Let's now start part 2 of this first lecture on artificial neural networks. And I will do so by talking first about some similarities and differences between learning in, on one hand, symbolic systems, which we spent some time on earlier on the course, and learning in sub-symbolic systems, which we will focus on this week. So, as you may remember, there are a variety of symbolic representations that we mentioned, some of them more, some of them less. Logical representations, functional representation, object-oriented ones, specific ones like production rules, decision trees, basic networks, semantic networks, and so on. The two sub-symbolic systems that we touch on this course are artificial neural networks, as for this week, and earlier mentioned also genetic algorithms. So, if we look at the differences here, one can say that when you implement learning mechanisms in a symbolic system, you do it normally as an add-on to a static kernel. So the static kernel is programmed, and then you add on these other mechanisms where you can adapt that static kernel to achieve adaptability. While in sub-symbolic systems, typically the learning mechanisms are the core of the system as a whole. So therefore, you get the impression, as is also true, that problem solving and learning are more tightly integrated or intertwined in a sub-symbolic system. So that is a clear pro of sub-symbolic system. There is also some con, and one of them clearly is the following, that what is learned and how it is learned is normally very concrete and explicit in symbolic systems. So you can actually look at the system before you learn and after, and you can see the difference, and you can actually more or less kind of read it. While in a sub-symbolic system, which are made up of these tiny processing elements, like a neuron or like a gene in the genetic algorithm, it's not trivial to see actually what has happened. And it turns out that at this moment, where some symbolic systems start to be used a lot, this is a key problem, and there are a lot of work in that area in order to interpret what has been learned, even if the system as such is very successful. Also, one can say there is a following difference. In a symbolic system, you literally reshape and extend current structures when you learn, which means that in a symbolic system, if you want extensive learning, changing the system not marginally but more drastically, you really have to make an extensive restoration of the system. You have to add things, you have to add structures, and that is not always trivial. The sub-symbolic approach is in that way very clever, because actually what you do is that you pre-allocate empty space, so to say. Because if you represent everything in a uniform form, you can say, okay, let's pre-allocate a lot of space for our system, but initially we only use a subset of it. And then we take the rest into use when it is needed. So one can say the structure is already there, but it's not used to its full extent. I mean, another can be actually when people talking about the brain or the mind is that the brain are used to a certain extent, but maybe not fully utilized, but because there are potential reserves in the brain neuron structure for more connections, you can take it into use. So there is this distinction between parameter learning and structural learning in machine learning, and I think one can phrase the approach in neural networks that you convert structural learning into parameter learning, and because parameter learning is normally considered simpler, that's a positive thing. If you only want to learn parameters in the first place, the differences between the symbolic system and the neural system is not so great. Learning in artificial neural networks is normally accomplished through an adaptive procedure known as a learning rule or algorithm, whereby the weights and also the biases of the network are incrementally adjusted. Potentially also other parameters, the so-called hyperparameters we talked about earlier, can be learned, and there are such. I mean, the function actually that controls the transfer or activation as an example of a parameter that can be modified. But there are also factors like learning rate and other parameters occurring in these models, and they are not part of the system in the sense that the basic learning rules handle them, but additional rules can be added for that purpose. For several reasons, the learning process is best viewed as an optimization process. You probably get the same picture again here. I mean, we have talked about this earlier. It's very common in artificial intelligence to look at things as a search process with the purpose of optimization. So actually here, what we do is we make a search in a multidimensional parameter weight space, where a tentative solution is gradually optimizes a pre-specified objective function. So the term objective function means that we have a function that maps an event, a situation, onto a real number, and intuitively many times it represents the cost for achieving what we have. So it could be then be called a cost function or a loss function. And of course, always we want to minimize the cost. However, one can design this in the opposite direction. So we can sell a cost function, we can have a reward function or a profit function, or a fitness function or something positive. And then of course that in that case, if we design it like that, then optimization is maximizing that kind of function. But it's all up to us how we want to engineer it. The choice of using artificial neural networks as a representation or something else is orthogonal to the categorization of machine learning techniques in supervised, reinforced, or unsupervised. So actually, ANN can be used for all of these kinds of three purposes. So for the supervised case, the input received from the environment is associated with a specific desired target pattern. So then the weights are synthesized gradually and updating when we treat data item per data item, so that when we went through the data set we have available, the weights have stabilized in such a way that they minimize the actual classification or regression error with respect to the predefined target reference point. But also neural networks can be used for unsupervised learning. It can be used for clustering. Of course, the architecture of that network that is fit for that purpose would be differently engineered. So So therefore, if you remember from this slide where you saw all the kinds of networks that is possible or have been designed, some of them are designed for the supervised case, while others are more typically designed for the unsupervised case. Finally, reinforcement learning can also be handled. And I would say that roughly the ANN architectures used for supervised learning can be rather easily adapted to the enforcement learning case. I mean, the difference essentially in the reinforcement case is that there is actually not a target reference for the value you want to achieve. It's rather a reward or grading from an external environmental or trainer on the quality of the result. But that can easily be remodeled in the same kind of framework as for the supervised learning case. Every artificial neural network model have different learning rules. So what I want to exemplify on this slide is actually just two common types. So what you see at the bottom is this, on this slide, is variants of what is called the delta learning rule. And the reason for the name delta is that at the center of this approach is that the updating of weights, because when we talk about learning here, we talk about normally updating of weights. So for the updating of weights, a key factor is the difference between the target output, the reference value, and the actual value produced by our network. So in the middle you can see T here, which is the target, and Y, which is the outcome. So the difference between those two, which we call the error of every problem-solving process, are at the core of the calculation of the next value. So it's the size. If it's a big difference, it will be a big change. If there is it also depends on the sign. So any kind of difference will affect the weights differently. Okay, so in contrast to that approach, which is widely known, and there are many versions of that, there is another style of updating, which I call here the Hebbian learning rule, which relates to this basic idea I mentioned from early idea by Donald Hebb, that what matters for the updating weight is the simultaneous compatibility of the firing of two connected neurons. So if they fire at the same time, that should be the basis for increasing the weight of that connection. But if they don't fire, or they fire in opposite directions, that should be the basis for diminishing or decreasing the value of the weight on that connection. So you can see there at the top you have the factor Y and X, which are actually the output from two neurons in that case. And as you can understand, if those values are compatible, have a positive value to increase the weight. If they are have an opposite direction, we will have a negative effect on the update. So these are two genres of updates, but as you can see, and that's the main message, is learning is updating on weights. Looking at the delta learning rule a little closer, and as mentioned, the delta learning rule is the kind of rule that controls the update of weights in a lot of cases. In general, for most cases, for what is called feed-forward ANN, which includes the perceptron, single-layer neural network, multiple-layer networks with backpropagation, and so on. So it's a pretty wide range of different designs where more or less the delta learning rule is used. And actually there are two main principles behind the delta learning rule. One principle is based on something called gradient descent, and there is also some way of calculating the error, which is the basis for the update, which is called, that approach is called the mean square error. So I will now shortly say something about these two phenomena. So the gradient descent approach or algorithm, it's an optimization algorithm for finding a minimum of a function. So we can also, sometimes it's called steep descent. The gradient is actually a multivariable generalization of the derivative. I mean, you have a space of many dimensions. I mean, in a two-dimensional space, you have the derivative, but in a higher space, you have its generalization. This means that you can take the derivative in different directions. It's a vector-valued function as opposed to a derivative, which is a scalar-valued one. And the gradient represents the slope of the tangent of the graph of the function. More precisely, the gradient points in the direction of the greatest rate of the increase of the function. To find a local minimum using gradient descent, one takes steps proportional to the negative of the gradient at the current point. So as I earlier mentioned, it's when we model our problem, we can model it as a minimization problem. We can probably model the same problem in another way, so that we can construct a maximization problem. So if you have model our problem in the later way, then we actually want to maximize our function. We want to climb. We don't want to go into a valley. We want to climb a hill. And in that sense, if we do it like that, then we can talk about gradient ascent rather than gradient descent, naturally. But I mean, the thinking is the same. I mean, there's also a technique we mentioned called hill climbing. And actually, hill climbing and or diving into a valley, in this case, are similar but not equivalent, because the pure gradient approach strictly prefers to go in the steepest direction. So if you are on a hill, you find the steepest point, while hill climbing selects the most promising next state. So I mean, if you have an analogy with a skier, probably the hill climbing, or its reverse, is more natural for a normal skier. You look down and you see how feasible it is to go somewhere. So if you find a feasible state, you try to find that. You don't necessarily go on the steepest point, actually, or rather the opposite. While steepest descent or gradient descent always go for the steepest road to go down. Both of these approaches are greedy, in the sense they do a local observation. You stand where you stand, and then you look around, and either you go for the steepest or you go for the best place. But you always take a local decision, which means that when you come further down, you may have seen that actually enough you want the wrong way, because if you view it from a global angle, there are deeper valleys or higher hills. The mean square error is a statistical measure that is pretty common. And actually, the mean square error is to look at a variable and a target value for that variable, and then compare that for the outcome of some measurement. And if you make a series of measurements of the same variable, you take the difference between the target value in each measurement, and you take the square of that, and then you get a series of squared errors, and you take the sum of that, and you divide by the number with how many measurements you have. So it's pretty straightforward. So this you can somehow apply in the context of an artificial neural network, where we look at the error between or the difference between the target value for an analysis process and really the output from the network. So if we have a single data item, it will look like simply the difference between the two scalars, the target and the outcome, and the square of that divided by 2. And if you take a series of values for a whole epoch, I mean, a number, you do this for a number of items, of course, you can then do as above, that to take the difference between all the outcomes from different data items, you square them, you sum them, you divide by n, and you divide by also by 2. So then you can ask the question, why do we divide by 2? And actually, that's an arbitrary choice. I mean, you can define an error method as you like. So you are inspired here, in this case, by the mean squared error method that you saw above. Why you divide by 2 is because if you take the derivative, which we typically do here, for example, in the delta method, then, as you know, the derivative of a square is 2 times the variable. So therefore, by dividing by 2, we get rid of the other 2. So this simplifies our calculation. So it's just put there for convenience. And it's arbitrary chosen, but for convenience. As I hope you have understood, I try to keep this course as little mathematical as I can. However, it's quite obvious that for the field of machine learning and artificial neural networks in particular, it's very difficult to keep entirely out of mathematics. So these things creep up. So I collected on this slide some areas from mathematics where it's very wise to have some prior knowledge if further studies of this subject is of interest. So matrices is an important area. Vectors, coupled to that, linearity issues, inner and outer products, measure of similarity, how you differentiate matrices and values, something called the chain rule of derivation, are important. And also some geometrical things are important, because many times you want to look at your search space, for example, with some geometrical or spatial views. Also graphs, of course, you can see in the end are important. The basic ideas and terminologies of graphs simplifies life. But I'm not going into this. I have to point at it, and I want you to understand that if you have a problem in some area, it would be wise to go back to some lectures or literature on these particular mathematical areas and make a little study there. Then you can continue with machine learning. It doesn't have to hinder you to go forward in this area. Artificial neural network is a complex area. So for that purpose, I really tried now for the purpose of this week to make a little map. So we now started. We talked about the fundamentals. So we are here, you can see, at the top. So below, you can see what we have before us this week. And as you can see in the middle, we will talk about what I will see the main stream of work in ANN, which is the kind of feed-forward networks where you strictly go from an input layer by a hidden layer to an output layer. To the right, you can see a kind of different tradition which is really inspired very much of what was already mentioned about Hebbian learning. So I would say that this genre of neural network we call associative memory. And I mean, there is no sharp boundary here, but roughly one can say that the right part here, the associative memory, is more related to handling unsupervised learning, while the feed-forward cases are more related to the genre of supervised learning. Reinforcement learning is more like in the middle, but I would say it's more natural to adapt the supervised learning method to handle reinforcement learning than the unsupervised case. However, artificial neural networks can be used in all cases, depending on how you engineer it. So the next two parts of this week is this part which is called recurrent neural networks, which essentially is about how to handle sequences in temporal data. And the third part, or the fourth part, is what is called convolutional neural network, which have to do with special mechanisms to handle perception issues, particularly imaging. So then in the end we will try to tie things together in lecture. So this is the structure we will follow. Finally, just a few words about the final point, deep learning. As I already said, it was invented in 1986. Actually, it wasn't used in 1986. It was only in 2000 that anybody used the term learning for related to artificial neural networks. And it actually wasn't widely used until 2012, when there were some real success stories by application of this kind of systems. And then the word deep learning was started to be used about this kind of systems. Now it's a dominating term, and one can discuss whether it's just a term for the state of the art in artificial neural network, or there's something more specific. And this we will discuss shortly in the final lecture. So that was the end of this lecture. Thank you very much. The next lecture, 6.2, will be on the topic of perceptrons.